Well, hello and welcome back. So today I want to do something a little bit different, not really continuing with the tutorial so much. I want to look at just doing a series of small little projects just to really explore fun things about programming. So a while back, as those of you who've been following my channel will know, I did a Halloween special where I used the Lorenz Attractor to create a potential Halloween mask. It wasn't really tremendously exciting, but it was something. I wrote that in C++. I did it using the libraries that I was in the process of putting together to support the ray tracing tutorial. Today I want to do something different. I want to go back to look at the Lorenz Attractor again, but we're going to do it in Python, and we're going to do it using Pygame, so that we can use that to make some cool animations and hopefully get some interesting results. So I don't want to talk for too long, really just want to jump into it, and yeah, let's go. So here at my desktop, the first thing I need to do is to set up Python. All right, then we need to make sure we have Pygame installed. Pip install Pygame. Okay, that's all done. So let's close test.py, close the welcome, we don't need that. Make a new file, I'm going to call lorenz.py. Okay. I just want to take a quick pause as we're writing this. We're creating a class that's going to handle our Lorenz system. The reasons for that I think will become obvious later. But one thing, just to talk about the equations, what we've implemented here are of course the classic Lorenz equations. If we look at those together, let's just make that a bit smaller. There we go, so we can see everything together. So the first equation, equation 1, is dx dt. It's a sigma y minus x. So sigma I've referred to as a, it's the first parameter, so that is sigma multiplied by y minus x, that's the same as that. And then we have dy by dt, it's x into rho minus z. Rho I've called b, so that's x multiplied by b minus z, all minus y. And we see we have the same there. And dz by dt is equal to xy minus cz, c being the equivalent of beta. So that's what we've done. Because we're using a simple method of dealing with these equations, we're just multiplying by dt, which is the time step, and simply incrementing x, y, and z respectively. So it's really the basic way of doing it. But there we go. That's what we're doing. So let's carry on. Okay, so that's basically what we're going to do. We have a class that defines our Lorenz system. Initially in this block of code and definite, we just set up all our initial parameters, x min and x max, the range on the x-axis, range on the y-axis, z min, z max, obviously range on the z-axis. We define our initial state. We create some other variables that we're going to need, ox, oy, and oz, which we're going to keep track of the previous point. X, y, and z will be the current point. dt is the time step. A, b, and c are the parameters of the Lorenz system, and we define the pixel color. We then have a step method. Every time that we call the step method, it will modify x, y, and z according to the equations that we've just described, and it will keep ox and oy and oz stored as the previous set of points, and then modify x, y, and z to be the new points. We can call every time we call the draw method, this will actually convert these, normalize these coordinates into actual screen coordinates using the convert to screen function that we've just defined here. Let's just put a space in there. So the convert to screen simply does the conversion from these ranges here to coordinates that will fit with our screen. So we do that for the previous position, the new position, and then we use Pygame's draw.line method to draw a line onto our display surface, which we're going to define in a moment, and we get a bounding rectangle. So we draw from the old position to the new position in the pixel color, the line of width 2. That's basically what we're going to do for Lorenz. That will become clear. So what we're going to do now is create the class for our application. So let's go. Okay, so that is everything. So in our application class, what we've done is we simply set up the parameters that we need here. We create an empty variable for our attractor. We may support more than one. We set our width and height to 1920 by 1080, set some other stuff. Okay, so we initialize Pygame, set the caption for our window. We call the display set mode method from Pygame that generates our display surface, gives us a thing of the right size. We set is running to true. And FPS clock is defined here. I'm not going to use it right now. We create an instance of our attractor class. On event, this is sort of standard Pygame stuff. So on event is a method that's simply called in our main loop. So in the on execute method that we have here, this is our main loop that runs continuously while the application is running, and it will loop through every event in from pygame.event.get, and we'll call the on event method that we've defined. If we get the quit method, then we know we want to stop, so we set is running to false, which would cause us to drop out of this loop, which would then execute pygame.quit. For each loop, we call the onLoop method followed by the onRender method. So onLoop calls the step method for the attractor, as we talked about. So in the attractor class, step calculates the new set of values for x, y, and z. And then we call onRender, and onRender is responsible for actually drawing it, and it calls the draw method for the attractor and passes the display surface as input, so it'll draw into that. And that's basically it. If we save that and run it, yes, there we go. We get one single attractor. So that's pretty cool. So pretty basic, but everything we need for a very simple implementation. So there we go. I mean, that's a very simple implementation, but it clearly works. It's everything we need to draw a very basic Lorenz attractor. What I want to look at is some of the more interesting things, particularly about the Lorenz attractor. And really I wanted to talk about the sensitivity to initial conditions, which is something that we haven't covered. And it's really one of the really interesting examples, and is the origin, I believe, of the so-called butterfly effect. You know, this idea that a butterfly flapping its wings in one country can then end up causing or being the cause of a tornado in another country. You know, Edward Lorenz in 1963 actually came up with these equations for the Lorenz attractor as a simplified model of atmospheric convection. It's quite interesting and quite apt given the talk of the so-called butterfly effect. But the reason that we talk about the butterfly effect, that comes from sensitivity to initial conditions of systems such as this. And what we can do is we can show, I'm going to set this up now so that we can plot more than one Lorenz attractor, and then we're going to have a look at what actually happens if we have a small variation to those initial conditions. And okay, let's dive in and do it. Okay, that should be everything that we need to do that. This is why we went to the effort of creating a class to handle the Lorenz system in the first place, because if we want to implement more than one of them, all we have to do is create multiple instances of that class. We do that here in the onInit method, where we simply create an empty array and we append a Lorenz system. We range from just in a loop from 0 to 3. So this will create 3 instances of the Lorenz attractor. We set them up with an initially random variation to the initial x coordinate, and we set them up to have each one to have a color picked from this color list. These happen to be the blue, orange, and yellow colors that I use for my channel branding, so I thought that would be quite appropriate. And then all we have to do now is on loop. We simply do for x in self.attractor, so x will go through each one of the attractors, and we call the step method for each one. And then on render, we modify so that we just call the draw method of each one in exactly the same way and call pygame.display.update each time. And that should be everything that we need to do. If we run that now, yes. So what we see initially is that we get just 2 attractors, but all 3 should be here, I think. But hopefully, yes, you see the orange one starts to separate later as we go. And what that shows is just how big of an impact a small variation in the original input parameters can actually have. If I run that again, let's just have a look. So we're talking really quite a small range of variations. I mean, actually that's probably quite big, isn't it? Let's do that, 0.01, minus 0.01 to 0.01, so that's really small. So what will happen is they should all be overlapping to begin with, and then over time they should separate. So let's run that. And they still end up going in different directions to begin with, because they're still very slightly different. So, I mean, that's a really tiny variation to the x-ordinate, but we still get that effect that to begin with, they vary quite enormously. Yeah, okay, we can make it even smaller. Yeah, so if we make the range of random variation really, really small, so what will happen is each of the three attractors is starting from a very, very slightly different position. But, I mean, the difference is really small, so they should initially all behave the same way. And what we will see is that over time they will diverge. So if we hit run, bad example. Yeah, they both. This is a slight difficulty with using random values, right, for the variation. Let's try that one more time. Now they still go off in different directions to start with. Okay, but what we see, it's we're talking a tiny, tiny variation to the input parameters is really causing all of this. I think part of the problem is that I'm ranging. We want to go from 0.1 to 0.101. Let's do that. Yes, there we go. So now they overlap to begin with. So they're all overlapping. And let's just see, as this runs, we should see that over time they will separate. Yes, and there we go. It didn't take very long. So we see the blue and the orange have now separated from the yellow, and as this runs, they will diverge further and further. And this is the origins, really, of the I believe, of the whole the principle of the butterfly effect. That just a very tiny change in initial conditions for a system like this can, over time, lead to wildly different results. And that's the basis. A really small change in or an immeasurably small change in a weather system somewhere, like a butterfly flapping its wings or something, could over time lead to a significant change in the weather in a different location. And really that's where it comes from, and I think that's pretty cool. Okay, so that's kind of cool, but one thing, we're only plotting this in 2 dimensions. Okay, that's a limitation. We know, because we define variables for x, y, and z, and we have the 3 equations for dx, dy, and dt, dx, dy, and dz, but we're only plotting in 2 dimensions because we've only got a flat screen. So we chose in this case to look at the x and y plane, which I think makes quite a nice illustration. If you want to change that, we just simply need to change what we plot here. So we're going from OX to OY. We could change that to go from OX to OZ, and there from X to Z. And then we need to change these to Zmin and Zmax, and the same there. Okay, and if we run that now, we should see it from a different angle. Yeah. And again, because we're starting to from the, we should see that they will continue for a while and then diverge. And there we go. That's actually kind of cool. Oh, do you know, actually, I think that looks cooler. Yeah. So that's rather fun. Okay, brilliant. Let's make a no. Okay. That is kind of cool. All right. So we can easily change that. Now, when I did this for the Halloween special episode, I did talk about how what we're doing here really is an approximation. So we are using just a very simple method of solving the system of differential equations, which is not necessarily accurate because it doesn't try to take into account in any way what happens to the system of equations in between each of our time steps. So if we make our delta t, the change in time at each step very, very, very small, we will then get progressively closer. But of course, what starts out as a tiny error will over time lead to greater differences, as we've seen. So what we can do instead is use a proper ODE solver. Since we're using Python, we're going to go ahead and install SciPy, which will give us access to such a thing. There's no need to write one ourselves. So let's jump in and do that. And I'm going to write the code to implement the same system, or basically just modify the class allow us to use the proper ODE solver. Let's jump in and do that now. So obviously, first of all, down here, we're going to do pip install SciPy. Okay, so just want to talk about that quickly. This is the function here now that implements our original system of equations. So as we know, let's just get these over here. So our first equation was sigma, or in my case a, multiplied by y minus x. So this is a times y minus x. And then we have x multiplied by, this will be a b for me, minus z minus y. So this is tx multiplied by b, or rho, minus z minus ty, and then we have xy minus beta z. Beta is c, apologies for the confusion, so tx times ty minus c times tz. So what we've done is created a simple function called f that has these input parameters that now defines our system of equations. For any input x, it will calculate dx dt as being the three values of that system of equations. Okay, and we're going to use that by feeding it into the ODE int. Okay, so just quickly want to talk about the solve method. So this uses ODE int, which is the method from SciPy, from the SciPy library, and we pass to that our function f that actually defines the differential equations. We pass to it our initial state. We pass to it the values of t over which we want to evaluate everything. So whereas previously we looped through it and we just incremented everything as we went, what we're going to do in this case is pre-calculate all of the time points, and then we're going to make the animation by simply looping through those time points in order to get what we want. So we're going to calculate all of the results up front and then simply loop through them to get the animation, and then we pass to it the arguments a, b and c. Okay, back to the code. Okay, so let's just save that. That should be actually everything that we need to define. So whereas before in our step method we simply calculated the next position and everything, what we're doing now, because the solve method now calculates every solution to our system, we are now simply computing x, y and z in our step method by extracting them from states. Okay, so states builds up as an array, so we do self.states equals ODE int, so all of the answers are stored, all of the solutions for every time point are stored in self.states, and then we just need to extract them in turn here as we call step, and that should allow us to create an animation. So all we need to do is then make sure that we use that, and we need to make it a slight change, so this needs to be a little bit different. So we're going to do self.attractors I. Instead of modifying x, we're now going to modify init x, but we're going to modify it in the same way, random.uniform 0.1 to 0.101. Otherwise, everything remains the same, which is kind of nice, shows why it's nice that we wrote the code the way that we did. And we need to modify here just on loop, we want to call x.step3 rather than x.step, so we're calling the new step method. But we also need to make sure that we, yes, one last thing, here we also need to do self.in this loop, we call attractors I, and we're going to call the solve method for each one. So as we loop through here, when we configure the attractors, we set them up with the initial point, we define the color, and then we call the solve method that will actually force it to run through and actually calculate all of the solutions. Okay, so we've modified our code here so that we're now going to be calling step 3. So if we save and run, we should now run using the proper ODE solver. Oh no, okay, what's wrong? Of course, yep, a range with a single R, because it's a range, not a range. My fault. Okay, if we run that now, we should be in business. Yes, and there we go. So now this is running using the proper ODE solver rather than the simple method we were doing before. So we can see it's a little bit slower. And just as before, initially we see that everything overlaps, but as it runs, after a certain amount of time, they start to diverge, and boom, there we go. We get the separation into the 3 different colors. And there we go. So this will run for the time points that we predefined. So it won't run forever, unlike the last one, but the code will mean that it will simply stop when it gets to the end. That was everything I wanted to talk about today. I really hope this has been interesting. Let me know what you think about the new format. I'm hoping to sort of go on with doing things in this way, making things a lot shorter, keeping it much punchier. So with the ray tracing tutorial that I did, everything was very long and really explained everything in great detail. There's very much a different objective with that. This is really just meant to be a bit of fun and look at how we can, you know, reignite that. I'm going to use the word childish enthusiasm for coding. When I was younger, I used to love writing code to do this kind of thing and just muck around with stuff. Python is very good for doing that. I mean, C++ is good for that too, but Python is just a bit easier, a bit more accessible. And yeah, I just, if I can inspire, you know, some of you guys just to play around and have some fun with coding, I think that would be great. Let me know in the comments what you think. Let me know if you have, you know, how you get on, if you create any interesting results with this or anything inspired by this that you've seen today. If you've liked this video, please remember to hit that like button, and of course please remember to subscribe to my channel so you don't have to miss any future videos. I'm hoping to run a series of videos from now on looking at doing this kind of thing. If this one seems to be successful, that's what I will do. And yes, we'll see how that goes. Anyway, it's been a pleasure. Thank you very much for watching, and I really look forward to seeing you in the next video. Bye.